Hey everyone, I'm Atticus, and I'm going to be talking about interpretability, just kind of the state of things where we are, and my thoughts on how we should be scaling it up, and maybe some issues that currently exist with how people are doing it. Okay, cool. So I'll just kind of hop in. So I think roughly a way to try to trisect what interpretability might be able to do for us is it might give us the ability to predict, control, and understand models. And I'm going to quickly go through kind of like each of these um, kind of topics and then talk to you about what I think are sort of the state of art methods for doing each of these things. And then I'll get to what it would look like to try to scale up interpretability. All right, so for prediction, really, I think it hasn't changed too much since pre-large language models and maybe like the 2016, like kind of like AlexNet era. It's just, you can just train another classifier on model internal representations to predict out a concept. So if a model has French text input, then you can train out a classifier like, what language is this text? And people have been doing this for a while. And you can also, think of this as just within information theory. So if you have an arbitrarily powerful probe, all probing is doing is measuring what is the mutual information content between a concept and then a hidden representation. And typically we train probes on like labeled input data, but you also might think about training a probe on what behavior a model will have. And that could be more relevant in a safety setting. But that's pretty much just, I think, the standard approach we have for predicting what models are thinking about, basically. All right, so then moving on to control. So control is a weird one, and I think steering has become a pretty popular way to think about interpretability and what we might be able to do with it. But I think a lot of the time we're not as eager to run the really strong, powerful baselines that we have for controlling a model, which are, one, fine-tuning. So if you could steer a model to make it an angry model now, or you could just fine-tune the model to be an angry model with some angry data, basically. And that we should be running these baselines so we can actually figure out, when fine-tuning isn't the thing we want to do. And so there's also parameter efficient fine-tuning, so fine-tuning can be really expensive, and I think that's why we might not want to do it. Yeah. And then we have prompt engineering, which is another very competitive method for controlling models. You can also just ask the model to be angry, or ask the model to speak in French, or ask it to talk about the Golden Gate Bridge. So these are, this is a really strong baseline for controlling the model, and it, is unclear to me like how much work it's going to take to get to a point where prompt engineering or fine-tuning isn't just the right way to go about manifesting some desired behavior in a model. And so methods like DSPy have the ability to even like automatically generate prompts for you given a specific goal. And it's just very cheap and easy to interact with. And so then we get to steering, which is, I think, really just a collection of methods that are focused on doing an intervention to some model representation, giving it a little tweak to then get some desired behavior, whether that's removing something or enabling something. And so a basic steering method is just, so maybe you have an angry text and then a bunch of angry texts and a bunch of calm texts. You run them through the model. You take the average angry representation, the average calm representation, find the difference between those two. And then that is a direction along which you can modulate the model representation to make it angrier or to make it calmer. So this is like a very basic supervised method for going about doing this, and this really would only work for binary concepts because you can't really do this in like a k-ary way, or I don't think I've seen anyone doing it, but maybe Andy will tell me I'm wrong or something. Yep. So yeah, here's just the example. I love talking about weddings. I hate talking about weddings. These are the contrast prompts, which are then used to steer a model. And so there are other simple ways to get the directions we would want to do steering. So maybe you train a linear probe, and whatever the direction that probe is sensitive to, that's also a thing you could use for steering, or dimensionality reduction techniques like PCA or SVD will provide you directions that, explain a lot of the variance of the data, and they might be useful to use. But really what I think for steering, the most crucial thing to do is just to establish a setting where steering is a good idea. I don't think that exists yet. And some ideas I have on what this might look like is if you're really overusing your prompt space. So maybe you have like 1,000 things that you want to cram into the prompt. Maybe some of those could be handled through steering and you give the model like more room to think. But I have not seen this yet, and I think that's basically where we need to go first in this research direction to motivate whether it's one we want to pursue at all. Yeah, and then last thing I want to mention, so representation fine-tuning is work that I'm involved with, and it's somewhere between parameter efficient fine-tuning and steering. So the sort of idea is that instead of just adding a vector to some hidden representation, you add a vector to the hidden representation, and then you also add a little adapter that is a low rank matrix transformation. And all that does is basically like read out a small amount of information and then inject a small amount of information at a specific location. So far, we've only benchmarked this method on just parameter efficient fine-tuning sort of things, so just like standard fine-tuning stuff. But I think where representation fine-tuning is going to shine the most is when we're trying to do surgically precise and like layered compositions of steering. Yeah. Yeah, and you can just kind of think that this is a way of taking the power of supervised machine learning and then using the targeted manipulations of steering. Cool. So prediction and control is not really what I would consider sort of like the core idea of mechanistic interpretability. And a lot of times when we talk about it in the field, we use words like basic science and reverse engineering neural networks into algorithms. And I personally think that my research and the research with my collaborators over the years take those sentences really seriously in a way I don't think a lot of other research in the area does. So we actually have a really mathematically and philosophically precise idea of when an algorithm is being realized by a deep learning model or really any dynamical system. Yeah, so I'll go through sort of just like how I think about what the like gold standard mech-interp looks like. So yeah, really this is just a general phenomenon. So we explain dynamical systems with the algorithms that they implement. So humans doing stuff, this is like the entirety of cognitive science and functionalist theory of mind, is that, yeah, we're something like computers and we can explain our behaviors and how we interact with something like an algorithm. And then we also have the same intuition probably about deep learning models. You know, if you're Gary Marcus, you never had this intuition about deep learning models, but it's one I've always had myself. And then also a physical computer, you know, the most canonical case of implementation, like that system is clearly one that implements a computational object. And it was something very cool for me in my undergraduate is basically realizing that this notion of algorithmic implementation, we just like hadn't precisified it basically. Like we didn't have the math and like the philosophy was pretty underdone. And basically, I think we do have an idea of talking about that, and we're made a lot of progress throughout my PhD and up to now on what it looks like for computational explanation to be good and for an algorithm to actually be realized by a system. So basically, our framework is that we represent a dynamical system and also a hypothesized algorithm as causal models. So all causal models are, they're just a bunch of circles and then arrows between those circles and then rules for determining the value of a circle based on its parents. It's just a discrete graph with some control flow structure to it, basically. And you can represent a neural network as that, where the variables are individual dimensions of vectors or entire vectors. There's lots of ways to do it. And you can also represent algorithmic flow and just algorithms with causal models. And so then, how do we understand the relationship between a simple causal model and a more complicated large causal model is with causal abstraction. And it's a pretty basic idea, and it's you just go through this high-level model with a small number of variables, and you say, where are they localized in the deep learning model? So you'll make claims about where the variables in the algorithm are being sort of causally realized or where information flow is sort of being mediated in the network. And then once now that we have the language to sort of like make these claims in the first place, the intervention experiments we do are going to be hypothesis testing and actually figuring out whether the hypothesis that we formed is accurate. So, yeah, and so we have, and so causal abstraction has these interesting origins in the last 10 or 15 years as like a mathematical field for supporting people who are analyzing weather data and also brain data. And I think we're actually much better suited to do this sort of analysis in interpretability in a really deep way. So this task of aggregating micro variables into macro variables, it's really hard with the weather and with the brain because we don't have interventional access to these objects. It is very expensive and very difficult to do even basic intervention experiments in these two settings. But we really have arbitrary precision and measure in this setting. We have like an ideal sort of like neuroscientist situation where we can manipulate and rerun and freeze and patch in whatever information we want. And so I think there's good reason that these new deep learning models that are so good are the first opportunity we have basically in human history to do this sort of hierarchical reverse engineering. And yeah, that's why I'm really excited about interpretability, and I think it's a promising and unique sort of like moment in history for us. Yeah, so the basic like recipe that we can walk through a little example for is, I'll walk through here. So basically the hypothesis you have about the structure of some neural network is a high level model and then an alignment between the high level variables and low level variables. So suppose we have just an algorithm that's adding together three numbers, X, Y, and Z, and we have a network that performs this. Then we have two runs of the network, 1, 2, and 3, 4, 5, and 6. The sum X plus Y is 3 on the left and is 9 on the right. If we do an intervention where we replace the 3 with a 9, the output should go up by 6. It's like a very obvious statement about this very simple algorithm for addition. But then what it means for these variables to be realized in the network is that if we do the corresponding intervention on the neural network hidden states, we get the same output. We get 12. So it's really a matter of aggregating a lot of these intervention experiments and showing that there's a counterfactual correspondence between quantities at the high level that are easily understood and these seemingly uninterpretable low-level hidden representations. And then I think one of the most exciting developments that has like come out of the research that I've been involved with is that we have a supervised gradient descent-based method for localizing concepts in this way. The very short idea is that you freeze the network parameters and then you learn an alignment between the high-level model and the low-level model. And that alignment is parameterized as a rotation matrix that basically tells you which linear subspaces of a representation you're going to do an intervention on. I'm not going to go into the details on that for the you can look at the paper, but basically the idea is that if you have the data, counterfactual data telling you what a network should do if a concept has been intervened on, you can then use that data as a signal to localize that concept to model internal representations. And if you want to do that, localized concepts, I really think this is the state-of-the-art method for doing so. Yeah. And yeah, so now I'm going to spend the end and I'm going to give my sort of like hot takes and thoughts on what we should be doing to scale interpretability and talk about sparse autoencoders briefly. All right, so just a refresher on what sparse autoencoders are. So sparse autoencoders are trained on the hidden representations of neural networks to reconstruct them. They project them into a high-dimensional space, and then they reconstruct that representation by projecting it down into a smaller space. And these are basically the methods that people have for featurizing the residual stream or vector representations in deep learning models. And so the typical SAE is just a linear layer followed by a ReLU, followed by another linear layer for decoding, and it is trained to just reconstruct the residual stream representations for tokens on a very large corpus. And features are automatically labeled using some auto-interpretability pipeline, and current pipelines really rely just on, here are some examples for which this feature activated, and that's how they label these features, these new directions in the residual stream space. Yeah, and so one thing I think SAEs would be good for is that they are unsupervised, so they might be able to come up with features we haven't thought of, but I really do think if you have a specific concept that you want to localize, SAEs will not be what you would ever use. You would, if you want to predict, you'd use a probe. You want to control, you'd use something like steering or reft. And if you want to understand, you'd use something like distributed alignment search. And that SAEs will basically never give you features that will be used in critical pipelines. Because if you can articulate what the feature needs to do, that's the same data you need to supervisedly train for that feature to get a better one. Yeah, and so here's what I want to see moving forward in scaling interpretability. First, I think it's really insane that our goal is to mechanistically understand an object using an SAE that has been trained only on the observational distribution of that object. It's like doing science without ever doing experiments, basically. Like, if we need mechanistic understanding, we need to simulate counterfactual states and networks with interventions, which we can very easily and cheaply do, and we need to incorporate that type of training data into our scaling efforts for interpretability. There's no reason to think that you could jump up a whole level of Pearl's causal hierarchy by just training on observational data, and now all of a sudden you've recovered a full mechanistic reverse engineering of an object. I think that's like the strongest problem I have with SAEs right now. Then we need to pre-register our criterion for success. We need benchmarks. We need to say what it would look like to be successful at a task, and then hold ourselves accountable if we're not able to meet that. I think that slipperiness is something you really want to avoid. SAEs have context-independent features, meaning they unpack the residual stream in the exact same way, no matter what the context you're in, and that is not an assumption I think you should make either. Also, I think we need to remain open-minded about nonlinear features. And yeah, I have been working on benchmarking interpretability methods, also have an alternative idea on how we should scale things up using counterfactual data, and I have some food for thought on nonlinear representations, but these are kind of like papers that I'm currently writing or about to be out, and I'd love to talk to you guys about them, yeah.
So the first question we have is there a way to use causal mediation analysis to benchmark SAE faithfulness?
Yeah, so I would say causal mediation analysis is exactly a special subcase of causal abstraction, and absolutely, we should be doing that. And the benchmark that I have on this slide, Rabble, is doing this. It's a benchmark for disentangling pieces of information and figuring out which components and features are causal mediators of that information.
Great. The next question is, your causal abstraction idea has been published since 2021. It's been fairly influential, and I think in the way people think about circuits, it's usually reflected, but people usually check whether hypotheses match the model in a very ad hoc way rather than using the full formalism. Do you think that's a problem? Do you think it should change? Where should things go here? Is it fine?
I think that's a really good question. Honestly, yeah, I like doing using the full formalism, I think is basically never necessary. You know, like formalism or math, if you can explain your ideas in a better way, you should totally go about doing it. But I do think that, say, Redwood Research is, I was a big fan of their interpretability stuff, but I think they really held themselves accountable for hypothesis testing. I think they were realistic about what failure looked like, and their conclusion was interpretability is really, really hard, and they didn't think it was going to be a viable way forward. I honestly think that, yeah, that is really the way we should be thinking about things. And I think some of the other interpretability efforts we see embrace the slipperiness of not having a defined criteria for success.
Let me check if there's another question, otherwise I have one. What do you mean exactly by intervention data? Observation data is equivalent to intervention data when all variables have been observed.
I don't think that's right in any way. Is that right? Okay, wait. What was the sentence?
Yeah. You can identify any causal estimate if you observed all the measured compounding. So in this particular scenario, you don't have anything that's unobserved or unmeasured. So observational data is like effectively the same as interventional data.
Yeah, so what I mean by interventional data is that the training data for SAEs are just the hidden representations, the values they take on when we put in an input. And what the data I think we need to have is once we put in an input and we let it run out, what happens when we do interventions on the hidden states in there, then what will happen? That's definitely data we don't have and don't use, and it's really easy to generate. Like,
Okay, excellent. Maybe one last question, if there is more. How well does distributed alignment search scale in terms of compute? What's the algorithmic complexity?
Yeah, I mean, the only trained parameters in distributed alignment search is the rotation matrix. So you had to, in the initial version of it, you had to sort of like choose a location you wanted to start doing your disentangling on. And then you would just train this sort of like just rotation matrix, which is just, or however many feet dimensions you're going to intervene on, that squared is basically what you want, or that times the dimensionality. But the HyperDAS, which is like this project that I've been working on, which is really thinking about like how do we scale up distributed alignment search in some crazy ways. And we're trying to do things with sort of like a hyper network that is able to select locations in the residual stream to do intervention experiments and have that network take in natural language commands about like the concept to localize. It's pretty ambitious, and the preprint is going to say basically like we put this end to end and the gradients worked and like it was able to be optimized to success in a very toy setting. But yeah, I think there's basically are alternatives to scaling interpretability that aren't SAEs, and that this is like food for thought about what they might look like.